When we talk about cause and effect, we often think in simple terms. One event leads to another. But the reality is far more intricate. Our world is composed of complex systems, networks of interdependent factors where multiple causes can converge to produce unexpected outcomes. In such systems, small changes can ripple through, creating disproportionately large effects. Today we'll explore how modern causal reasoning tackles the challenges posed by these systems, and look at how quantum decision theory offers a new lens for understanding uncertainty and causality. Imagine a global financial market. The rise and fall of stock prices aren't driven by one single factor. Instead, they are shaped by an interconnected web of political decisions, economic trends, technological innovation, and human psychology. In complex systems, these variables interact in ways that are non-linear, making cause and effect much harder to pin down. Take the example of the butterfly effect, a concept from chaos theory. A butterfly flapping its wings in Brazil could set off a tornado in Texas weeks later. While this might sound hyperbolic, the principle it represents is essential. In complex systems, tiny inputs can result in massive, unforeseen changes. This poses a problem for traditional causal reasoning, which is often based on linear, predictable relationships. In such systems, multiple causal chains exist, but they often overlap, intertwine, and obscure each other. Emergent properties, behaviors of the system that are not obvious from the individual components, complicate the ability to attribute outcomes to specific causes. For instance, the 2008 financial crisis wasn't caused by one event, but by a series of interconnected failures in housing markets, regulatory oversight, and global economic policy. This brings us to a critical point. Classical causal reasoning often struggles in the face of such complexity. When we think about causality in simple systems like a ball rolling down a hill, we can easily draw a straight line from cause to effect. But in complex systems, the variables are so numerous and the interactions so unpredictable that finding a single definitive cause becomes nearly impossible. Moreover, in such systems, feedback loops further obscure causality. A cause might lead to an effect, but that effect could in turn influence the original cause, creating a recursive relationship. For example, in climate science, increased global temperatures can cause ice caps to melt, which in turn reduces the Earth's ability to reflect sunlight, further accelerating temperature increases. These self-reinforcing loops defy simple causal explanations. Causality in quantum decision theory. But complexity isn't the only challenge to our understanding of causality. As we delve into the world of quantum mechanics, the very notion of cause and effect is called into question. At the quantum level, particles don't behave in predictable ways. Instead, their actions are governed by probability distributions, and the outcome of an event isn't fixed until it's observed. This has profound implications for decision theory. In classical decision theory, we assume that we can predict outcomes based on past information and causal relationships, but in the quantum world, uncertainty is baked into the fabric of reality. The quantum realm introduces us to the idea of superposition, where particles can exist in multiple states simultaneously. This raises a fundamental question. How can we reason about causality when outcomes are probabilistic and unknowable until observed? In quantum decision theory, we shift our approach. Instead of assuming fixed outcomes, we deal with probability amplitudes. Decisions aren't about choosing between concrete futures, but between a set of probabilities. Consider Schrödinger's cat, a famous thought experiment. The cat is neither dead nor alive until we open the box and observe it. In a similar vein, decisions made in quantum contexts aren't finalized until all potential outcomes collapse into one reality. Non-locality and quantum entanglement, challenging causality. Another key challenge to traditional causality comes from the phenomenon of quantum entanglement. When two particles become entangled, the state of one particle is instantly correlated with the state of the other, no matter the distance between them. This defies classical notions of causality, where an effect must have a direct, local cause. Einstein famously called this spooky action at a distance, but it has since been verified through numerous experiments. Entanglement challenges our very understanding of how information and influence travel between objects. In the classical world, causality is mediated by physical interactions. But in the quantum world, the influence between entangled particles appears to transcend space and time. This non-locality forces us to reconsider what it means for one event to cause another. Quantum causality in artificial intelligence and big data. Now, let's bring this discussion into the modern world of technology. In the age of big data and artificial intelligence, we're tasked with analyzing vast, complex data sets where traditional causal models often break down. AI systems, particularly those using Bayesian networks and causal inference models, are designed to uncover hidden relationships between variables, relationships that might not be apparent through human reasoning alone. But what happens when we apply quantum principles to AI? Some researchers are exploring the use of quantum algorithms to process data in ways that classical computers cannot. Quantum computing has the potential to simulate complex systems more accurately, taking into account the uncertainty and non-linearity inherent in both the quantum and classical worlds. Imagine an AI system that can analyze financial markets or climate data, not by drawing straightforward cause and effect relationships, but by calculating probabilities across vast networks of interconnected events. Quantum AI could revolutionize our ability to understand and predict outcomes in complex systems, offering a new frontier in both decision-making and causal reasoning. Rethinking causality in the modern world. As we've seen, traditional causal reasoning is a powerful tool, but it struggles in the face of complexity and uncertainty. Whether we're dealing with the unpredictable interactions in global systems or the inherent randomness of the quantum world, our understanding of causality must evolve. Quantum decision theory and the study of complex systems offer us new ways to think about cause and effect, moving beyond the limitations of linear deterministic models. In the future, as AI continues to develop and quantum computing becomes more accessible, we will likely see a fusion of these fields, providing us with even deeper insights into the nature of causality and decision-making. By embracing uncertainty and complexity, we open the door to a richer, more nuanced understanding of the world.